I'm Joe Groff. I'm here with Doug Gregor. We both work on the Swift compiler at Apple, and we're here to share our experience optimizing runtime metadata for the Swift runtime. We think this will be generally interesting to language implementers because most compilers, in addition to generating the assembly language for your program, also need some sorts of implicit global data structures to support language features. C++ errs on the static side, but it still has vtables to support virtual functions, has runtime metadata to support exception handling and dynamic casting, and also has unwind table to support exception handling. Other languages tend to want to do a little bit more than C++. Some other common features are richer introspection, having preserving more metadata about like what properties and what methods your types have so you can work with them at runtime. If you have a garbage collected language, usually you need some sort of metadata to be able to chase pointers and figure out what your life set is. And for .NET languages and for Swift, you want to be able to instantiate reified generics at runtime as well. And all of these need metadata structures. And one thing these metadata structures all tend to have in common is that they're full of pointers. They form dense object graphs, and pointers are the most obvious way of representing that. If we look at the metadata generated for a small C++ class like this, it's going to have a vtable, and that vtable is, of course, going to have pointers to all its method implementations. But then it's also going to have a pointer to its RTTI record, which in turn is going to have pointers to its name and its base class, which in turn is going to have yet more pointers to its base class all the way up the inheritance chain. And while C is kind of trained us to think of pointers as being this bare metal, free abstraction, when they appear in global data structures, they create a problem for the dynamic linker. When you map a dynamic library into a process, you can't know where in the address space that dynamic library is going to end up. It could be linked with any number of other dynamic libraries. So what we have to do is record placeholders for all these pointers, and a dynamic linker has to fix those up at load time. And in the process, what that does is it dirties the memory, which separates the connection between those pages in memory and on disk. So there are all these hidden costs to having these global data structures full of pointers. It takes time to relocate all these, and that delays the start of your actual program. By dirtying the memory, we've increased the memory use of the entire system. We can no longer share these pages among processes that share the same dynamic libraries. It also increases the file size cost of these data structures. Not only do you have to have the in-memory representation, but you also have to pay for all the relocation data in order to fix it up at load time. And while in a large framework or in a large program, you probably end up using a different cross-section of the classes in that program in any one execution, the dynamic linker doesn't know that, and it has to do all this work up front regardless of what your program actually uses. And these costs are made even worse by a lot of properties of modern platforms. For example, we have mostly 64-bit platforms these days, and that doubles the size of all your pointers, and in turn, all your pointer-laden data structures. We encourage ASLR on a lot of platforms for security reasons, and that in turn makes even your executable have an unknown base address. So you pay for all these costs even in your executable. So users love dynamic language features, but they don't want to pay for them. One approach we could do is we could take C++'s don't pay for what you don't use to its logical conclusion with regards to metadata, only providing metadata for the things where you ask for them. In C++, if your class doesn't have any virtual methods, you get no metadata at all. It's just a struct. And when you do get metadata, it's extremely limited. It basically supports only the features C++ has. You can do exception handling, you can do dynamic cast, and that's about it. That's all you can do with RTTI. And the issue with this austerity approach is that austerity doesn't work very well. You end up with metadata that's, while it's small, it's so limited that users don't even want to pay for what's left. And we see this with, for example, LLVM just flat out turning off RTTI and reinventing it on its own terms. So if we want to make metadata useful and we want to build language features that can rely on it being there, we can't really take that sort of minimal approach. The metadata needs to have enough information to be able to support powerful language features, and we need to be able to rely on it being there. And in order to do that, we need to somehow mitigate these costs to the point that developers are willing to pay for them in their binaries. And we think we got there with Swift. By using the techniques we're going to talk about in this presentation, we got to the point where Swift programs can include runtime metadata, all of their runtime metadata by default. While we were implementing these techniques in Swift, the Chrome project also investigated using these techniques for C++, and they found that even with C++'s more limited metadata, they got some pretty interesting gains. Even though they didn't get to shipping, they had some really promising results. So we think anyone who's interested in bringing up their own language implementation or even bringing up C++ or an existing language for a new platform without legacy concerns might be interested in taking this approach to their global runtime metadata structures. The key thing that we built our metadata structures on in Swift was the idea of relative references. Most of those dynamic linking costs we talked about come from the nature of pointers. Because a pointer points to an absolute address in the address space, it's really tied to that specific process and its memory map. If you map something to a different base address, then all those existing pointer values are invalid and can't be used anymore. However, dynamic linkers generally slide a dynamic library or an executable as one unit. Only the base address changes, and the relative distances between objects in that image doesn't change. So if we use relative addresses, measuring the distance between objects, then we can slide those around in memory, and we can record those offsets in the binary, and we don't have to do any work. This directly mitigates a lot of those secondary costs that we talked about with dynamic linking. We don't have to pay for any additional startup costs. The pages remain clean, so they can be mapped on demand, and we don't have to record any relocation information in the final image. Furthermore, we can take advantage of the fact that most images tend to be 2 GB or less and shrink our relative references down to be 32-bit, which reduces the size of a lot of data structures in half. There's a lot of different approaches you could take to relative referencing, a lot of different reference points you could use. The one we found worked best for Swift was to use the address of where the offset was stored itself. And this has a lot of benefits. If we want to write a C++ code that interacts with our compiler-generated data structures, say we're building a runtime for our language, we might, if we had to deal with a C++ vtable from C++, represent it something like this struct here, using the traditional pointer-laden approach. If we wanted to move to using relative references, we could write a wrapper class that presents the pointer interface but uses a relative reference as its in-memory representation. In order to go back to an absolute pointer, we take the address of where that offset is stored and add the offset to it. And then we can transition to relative pointers by changing all those C++ pointers into our smart pointer class, and our user code doesn't have to change. When we're implementing our compiler, we can take advantage of the fact that most existing object formats already support subtraction relocations or PC relative relocations when we're generating our assembly code. The LLVM assembler supports subtractions, and these get mapped to the right thing at the object format so that your image gets the relative reference when you link all those object files together. Furthermore, there's even a nicer shorthand syntax for referring to the current location. Now, to resolve a relative reference does require a code size trade-off in your code. It does take a little bit more math to add that offset back to the address. But it doesn't require any more memory traffic. Your load dependency chain doesn't change. So taking advantage of out-of-order execution, that extra overhead is not generally noticeable. If you're writing your compiler in LLVM, you can take advantage of relative references as well. It's not quite as nice as assembly language. Unfortunately, there's no direct support for subtracting two pointers in LLVM. There's no pointer sub instruction, as it were. But what we can do is convert both the reference and the address of it into integers, subtract those, and then truncate that down to the desired 32-bit result. And although it's a rather verbose notation, it lets us represent a relative reference in LLVM. So using relative references really saved us a lot of overhead, and it was a great trick for handling intra-image references, where we could take advantage of the fact that we didn't need to relocate them at runtime. However, there's still some complications having to do with referencing things across images, which Doug is going to come up and talk to you about right now.
Thank you, Joe.
Thanks.
All right. So when we're building a typical app, we're probably using some form of shared libraries. And relative references are absolutely wonderful within those shared libraries and within the application themselves, so you get clean pages there. But you're still going to have some kinds of references that cross over different images. And when you go ahead and, say, slide things in memory, those are going to have to be patched up by the loader. And so we need to build something that takes the ideas of relative references and also can work across images. So let's step back, because this isn't actually a new problem. This is something LLVM does for you basically all the time, even in simple C code. So the C code on the left here just declares a global variable in our own source file and then modifies it. And you can see the assembler on the right-hand side. And the assembler is very straightforward, just referring to foo and moving the value into it. The RIP here is because, of course, we're building position-independent code. So let's make a very small change to the C code and say, well, now foo is an external integer. Small change in C. Now it's just going to be represented in LLVM as an extern global, but we get a very different code sequence here. You see this really interesting @gotpcrel thing. This is referring to the GOT, or the global offset table. But you also see that we have two move instructions. And what we're effectively doing here is moving the address of foo, which we get out of the global offset table, and then storing our value, the 1738, into that address that we loaded. So one move has become two because we're crossing over to another image, potentially, and we need to get the address of the thing we're referencing. It's as if in C, we had gone ahead and created a new local variable, this adder of foo, that's a pointer constant referring out to the address of foo, and then rewritten every reference to foo that shows up in our program as a dereference of that pointer adder to foo. That's what LLVM is doing for you behind the scenes. But we can make this explicit in LLVM IR to help us refer to metadata that might be in a different image. And so here we've made foo an external constant, and we've represented the adder of foo as a hidden unnamed adder constant. So of course it's a constant, we're referring to some address, although the loader's going to fix that up for us. Unnamed adder says we don't really care about the identity of this adder of foo thing itself, we only care about what it points to. And so that allows LLVM to coalesce all the different references to foo into just a single place. Now LLVM is even smart enough to coalesce it into the implicitly generated GOT, the global offset table, so that it's all co-located in just a couple of pages to reduce load time and keep these pointers from being scattered throughout your image. Now the whole reason for doing this, of course, is now we have this adder of foo thing that we know is in our local image, and so we can build relative references to it. We'll do that by introducing another one of these smart pointers. So Joe talked about the relative direct pointer, which is relatively referencing something that's in your image. This is the relative indirect pointer. So it's not referring directly to the thing we want, it's referring to a pointer to the thing we want, which might be in the global offset table. So we have the relative offset pointing at this adder of foo, and then we dereference again to go get to foo itself. And so the linker and loader has to deal with patching up the address of foo in green here, but not the rest. So we have two kinds of references here. We have the direct and the indirect references. When do you use each? You would like to use the direct relative references whenever you can. These are most efficient. They have no relocations whatsoever. But you can only use them for things that you absolutely know are image local, because they fall apart, they break at link time if you can't actually find the symbol. You can use indirect relative references when you're referring to something that might be non-local, because there is something in the global offset table that can be patched up by the loader there. Now, you could also use indirect references if your relative references are based on 32-bit offsets, and you may actually be building greater than 2 GB images if you're in that world. Generally, we haven't had to do this in our work. So now that we have both the direct and indirect references, let's go ahead and walk back to our C++ vtable example and talk about where we'd use each one of them and why. So again, here's our class foo. It just has one base class and a couple virtual functions in it. And so we're going to lay out the foo vtable, and we see we have a mix of direct and indirect pointers in these data structures. So we're going to use direct pointers for the RTTI structure here, the second struct, and also the type name. Now the reason we know that we can do that is because you always emit the RTTI structure and the type name alongside the vtable. It's there in the same translation unit. They're all part of the same metadata. And so it's guaranteed to be within our image. So we can just we can do a direct reference to it. Now, on the other hand, with the base class, we're going to use the relative indirect pointer, because it's a pretty common pattern to write a class in your own program that is a subclass of some type, of some class that's defined in another shared library that you're going to link in. And we have to deal with these cross-image references. Finally, we have the destructor, a virtual destructor, and the virtual function here. And we're going to use relative direct pointers. So the reason we're going to do this is, generally speaking, all the implementations for the class should be in the same image as the class itself. Now, if for some reason you have a strange class where this is actually not true, the way you would address this in your compiler is to emit a thunk. So you emit a little function into your own image that you can directly reference from the vtable. And all that function does is call out to the actual definition of the real foo function, whatever it is, that might be in another image. Now, there's one little unfortunate inefficiency here. The base class certainly could be in another image, but a lot of the time you're subclassing your own classes and you know that they're in that actual image. So we've added this extra level of indirection that's costing us a God entry and a little bit more code, but shouldn't actually be necessary. And so we'll introduce sort of 1/3 smart pointer for dealing with relative references. We're going to call this the relative indirectable pointer. So this can be direct or it can be indirect. And the way we're going to encode which of those it is by using the low bit of the offset as a discriminator bit. When this low bit is set, we put ourselves into the indirect case. So the offset relative to where this pointer is stored is actually referring to the pointer to the thing we actually want. And so we have the double indirection in this case. When the low bit is clear, we're in the more efficient direct case. And so we just need to do the offset from our this and then cast once. We don't actually need another level of indirection there to refer to the thing. And so in this case, we can use our notion of indirect relative references to decide at code generation time where the symbol is going to be and get the most efficient encoding. Now, there's one thing to take care of here, in that we're using the low bit of the offset as a discriminator bit. So we need to make sure that the thing we're referring to is at an even alignment. So it's not going to use that bit to actually refer to a valid part of the pointer value. A special case of this to really watch out for is that functions are not aligned. And so particularly if you're using, say, arm with thumb, those functions could certainly be at an odd offset. So don't use the relative indirectable pointer with functions ever. OK, so we can bring this relative indirectable pointer back and use it for our base class. And this sort of gives us the best of both worlds. So the base here can refer to a class that's in another image, and that's fine. It'll go through one level of indirection. Alternatively, if the base class is in your own image, you can refer directly to it and then save yourself the God entry. OK, so we've talked through relative references, how to make them work within an image, across images, to try to make metadata more efficient. Now, one of the nice things about relative references is they can actually be really good for tooling when you're building your tooling based on them. And that's for one very simple reason, that the metadata that you build out of relative references is constant, and it doesn't matter what process you're in, you can still read it and interpret it in the exact same way. And so this means it's really easy for tools like your debuggers and your profilers that work out of process to reason about your metadata when it's built this way. And in fact, you don't even need a process. So you can build metadata dumpers that interpret this data just by looking at the binary on disk. And they're fairly easy to build and can build on top of these smart pointers that we showed as well. So I'm just going to talk about one of these tools that we've built in the Swift world, and that is the remote mirrors library. So remote mirrors is about inspecting a process remotely, so from at least another address space, maybe on a different device. And it can read and interpret the metadata from that process to learn things about it. For example, it can compute the layout of the types that are used in that process just from that metadata, and use that to go inspect the values that are in that process. This is fantastic for a debugger, which wants to look at another process and figure out what's there without ever running any code in the process. Now, this is what debuggers do, right? This is what LLVM does, but often they do it based on dwarf type encodings, which is sort of a lossy encoding of the actual programming language semantics. Going through remote mirrors, we're depending on the exact same metadata that supports the whole Swift runtime and the entire ecosystem. It has to be there, and it has to be correct. It's part of the program. And so we can get a much higher fidelity debugging experience by building it on top of this relative metadata. So the idea behind relative references is that we want to make metadata cheaper so that we can use it more in our programming languages. And there's a couple of ways we do that. So relative references, when we're using 32-bit offsets, provide smaller code size versus 64-bit pointers. That's great. Those metadata segments, those are read-only. There's no relocations that show up within those segments. So that eliminates dirty pages and it reduces the amount of work the loader has to do to patch up pointers. So startup costs go down. That metadata is there, but it's not costing you as much at load time. It just exists in the binary until it's used. Now, whether we've done enough with these techniques to make metadata efficient enough to be ubiquitous, it really depends on your programming language and the expectations of your users. But we have a couple of interesting data points here. So Joe had mentioned the C++ relative ABI prototype that they're working on for Chrome, and the savings there was 9%. In C++, which we already talked about is kind of austere with the actual metadata it generates, it was still 9%. And Peter Collingborn, who worked on this, noted that a lot of this comes from just, we have many, many, many fewer relocations in the resulting binaries. On the Swift side, we've done this throughout all of our metadata, and it's made the metadata small enough and cheap enough that we feel comfortable turning on metadata by default everywhere and building interesting language features on top of that, like reflection and so on. And we hope to do more of that in the future. So thank you very much. Do you have any questions?
Time for a question, perhaps?
Did we go over?
Yeah.
Thanks for the. Oh.
Okay.
Thanks for the great talk. So I don't know if I got it correctly, but it seems that the solution for the indirect references should be done more in during the linking phase, right? So if during the linking phase you will know that you are calling something in the same unit actually, right? So have you thought about moving it, or it's too difficult?
I mean, we've kind of been like focused mostly on just getting the right ABI lately. So we've been doing what we can with the existing tools. But that would be a really interesting thing to explore, is like having the linker do this for us, so that the compiler doesn't have to have like kind of premonition of what's going to be linked against.
Okay. Okay. Thank you.
All right. Thanks again. We'll be starting up in about 5 minutes.
All right. Thanks everyone.
Thank you.